So we've already looked at the dot product, which is sort of one way of thinking about multiplying two vectors together. The cross product is another way of thinking about multiplying two vectors together. And unlike the dot product, the cross product does use the multiplication symbol. So A crossed with B, and we use the times symbol. Unlike this dot product return to scalar, the cross product is going to return a vector. And sometimes the cross product is called the vector product instead of the cross product, but I'll always call it the cross product. Now we're going to start off with sort of a geometric interpretation of what a cross product looks like. So imagine you have two vectors, A and B. If you cross them together, the cross product will return a new vector, and that new vector will be perpendicular to both A and B. So then I always like to ask students, well, what does that vector look like if it's going to be perpendicular to A and B? So, I mean, this could be A right here, and this could be B right here. Well, if it's perpendicular to B, then you might think it looks like that, but then it wouldn't be perpendicular to A, so that doesn't work. So you might try putting it here. Well, that's not perpendicular to A either, so that doesn't work. If you make a vector perpendicular to A, okay, it's no longer perpendicular to B though. There's actually only one choice in this example. That's that the vector is going to either have to come out of the screen or go into the screen. So you could draw a vector, and if I was at the blackboard right now, I'd literally put the meter stick on the blackboard and show you that if I put a meter stick directly on the blackboard, I've created a vector that's perpendicular to every single vector I could draw on the blackboard or the whiteboard. So you can actually see my pen right here, maybe. Okay, any vector you draw on the computer screen right now is going to be perpendicular to this vector I've drawn right there. So that's why cross product is only defined in three space. You can't have two. You can't take the cross product of a vectors on a plane. There's just no such thing. Now you might be wondering, well, if the vectors are collinear, then you could come up with a vector perpendicular to both of them. Yes, you could, but that doesn't always happen, and we're going to talk about what happens to the cross product when your vectors are collinear. So this picture gives you a pretty good idea right here. So we can see vector A and B drawn here, okay, on the same flat surface, but this flat surface is now not the screen. It's kind of a plane that's perpendicular to the screen, and then A crossed with B would be this vector right here. Now, if A is A1, A2, A3, and B is B1, B2, B3, here is the definition of the cross product. Now, that's pretty nasty looking. I mean, if we were in class, I don't give you this formula when you write a test or the exam. You won't be given that. It looks hard to memorize, but it's actually not. In fact, there's an easy way to do it. So what we can do, I'm going to show you how you can get this formula right here very easily. And don't worry about why it works yet. We'll get into that in just a second. So what you do is, notice I write vector A twice, just like so. And then down below, I'll write the same thing with vector B twice. Okay. Then what I do is I take the first and last and I just sort of ignore them. And you can kind of see the formula is here. If I go A2 times B3 and subtract A3 B2, there's you get that part of the formula right there. The second value of the formula, A3 B1 minus A1 B3, is right here. A3 times B1, subtract A1 times B3. And then finally the last coordinate, A1 B2, A1 times B2, subtract A2 B1. There it is right there. So it tends to be that you don't use this formula too often. What you do is you write the vectors twice on top of each other like I've done right here, and then you do this little trick. There are other tricks to calculating cross products easier. Your textbook has a different one, though I find it to be quite a bit more confusing. So let's just look at an example to start. Okay, so simple example, we want to find U crossed with V. So UV, when I do U cross with V, I'll get a new vector that's perpendicular to both U and V. But there's only one vector that is U cross with V. You do have to use this formula. Now you don't actually have to use this formula, but the resulting vector we're going to get is going to be from this formula. Now, rather than actually using the formula the way it is, this is what I recommend we do, that we write vector U twice, 1, 2, -4, 1, 2, negative 4. We do the same thing with v. 2, negative 3, 1, 2, negative 3, 1. Okay, take the first and the last and just kind of scribble them out. And then this idea of going 2 times 1, subtract negative 3 times negative 4. So u crossed with v will be equal to, the first coordinate is going to be 2, subtract negative 4 times negative 3. Now, negative 4 times negative 3 is 12. So 2 subtract 12 is negative 10. The next coordinate will be negative 4 times 2, subtract 1. So negative 8 minus 1 is negative 9. And 1 times negative 3, which is negative 3, subtract 4 is negative 7. And there we have it right there. So this little trick gives me this formula a lot easier than using this formula. Having said that, it is easy to make mistakes when doing the cross product, okay? Especially with mixing up the signs. The dot product is a lot easier. Now, I know that this vector u crossed with v, let's call that, I'll call it x. So let x equal u crossed with v, which is that answer we found there. It's easy to make a mistake. But I know vector x needs to be perpendicular to both u and v. And it's easy to check to see that it is perpendicular because the dot product's a lot easier. We know that x dotted with u better be equal to 0 if they're perpendicular. And if they're not, if this isn't true, then I probably made a mistake. And dotting can almost be done in your head. I'll do it here. 10, negative 9, negative 7. I might have made a mistake even. I'm not going to back up the video if I made a mistake. 1, 2, negative 4. Do I get 0 when I do that? Let's see. I would get negative 10, okay? Negative 10 minus 18, which is negative 28, but then plus 28, yes, checks out. How about x dotted with v? Does that equal 0? Well, 10, negative 9, negative 7, dotted with the second vector, v was 2, negative 3, 1. What do we get when we do that? Let's see, we would get negative 20 plus, negative 19 is 27, so plus 27 is 7, minus 7 gives us 0. So yes, it does work. So there's our new vector. It's perpendicular to both u and v. Let's take a read this statement here. If a and b are non-collinear vectors in R3, so that means assume a and b are not collinear, okay? Then every vector perpendicular to both a and b will be of the form k, a cross with b for some k er. So basically what this is saying is if you have vectors a and b, I'll draw them like this, okay? Any vector that's perpendicular to both a and b has to be some scalar multiple of the cross product. So in this example, maybe the cross product is this vector right here. Well, all the vectors perpendicular to a and b are collinear to this vector, okay, or are some scalar multiple of that vector. It's all that is saying. So you want a vector perpendicular to a and b if a and b aren't collinear. You're going to get some multiple of the cross product. It's the only way to do it. Now, the cross product itself is some specific vector. It is a vector, okay? There's only one cross product. If I say find the cross product of a and b, there's one answer, okay? Even though there's a bunch of vectors that are perpendicular, and they're all scalar multiples of a cross with b. How did they come up with the cross product formula? Well, if you like, you could look in your textbook, and they do explain how they come up with this formula. It's pretty long. It's a little bit complicated. To me, I'm more of a fan of, look, somebody's come up with that. We can prove that it works. For example, if I have that A is equal to A1, A2, A3, and B is equal to B1, B2, B3, then according to the formula from the first page, if V is equal to A cross with B, then V is this vector right here. I can dot A with V and show that A and V are in fact perpendicular. Okay, so what I would get then is I would get A1, okay, times the first coordinate of v, which is a2, b3, subtract a3, b2, plus, and I do the same thing with a2 and the second coordinate, a3, b1, subtract a1, b3. And for the last one, a3 times the last coordinate, a1, b2, subtract a2, b1. There we go. Let's expand that and see what we get. There you have it. That's a little long, but this is really just the distributive property. Now, what happens after that? Well, notice that we have, I've written them, to make it a little easier, I've written them all alphabetically. A1, A2, B3 minus A, do I have anything else like that? A1, A2, B3, sure enough, here and here are the negatives of each other. I have an A1, A3, B2, there's a negative of that and an adding, and then look at the last two cancel out as well, and sure enough we get 0. Therefore A and V are in fact perpendicular vectors. Now I'm gonna leave this to you. Go ahead and do the same thing with vector B, dot it with V, and you'll find you also get 0. So when you see it this way, it's not that complicated. Although this is a complicated formula, you can see it's the perfect formula. That means when you take this vector and dot it with A, you get 0. You take this vector and dot it with B, you'll get 0 as well. So it works. Here's a common thing that you need to do. Find vectors that are perpendicular to two other vectors. I know that seems kind of odd that we would need that, but the cross product comes in handy a lot later on. We use vectors in the second unit of this course to talk about lines and planes in 3-space. And so this is kind of where some of this stuff is going. So I want 3 vectors perpendicular to both x and y. Well, I know that the cross product will give me 1 vector perpendicular to both x and y. In fact, I know all the vectors perpendicular to x and y are going to be some multiple of the cross product. I can clearly see that x and y are not collinear, by the way. Okay, so we will start by saying, looking at what x crossed with y is equal to. So to do that, I'm going to write 840 twice. Okay, and I'm going to do the same thing with y, negative 216, negative 216. Get rid of that and get rid of that, and away I go. 4 times 6 is 24, subtract 0 is just 24. So I've done this one right here, 4 times 6, 0 times 1. Next I move on to this, 0 times negative 2, 0. Subtract 8 times 6 is negative 48. Okay, and then 8 times 1 is 8. But 8 subtract negative 8 is 8 plus 8, which is 16. So there's the cross product. Now you may want to double check and make sure that when you dot it with x and y, you do get 0. So if I take that vector, 24 times 8, I'm dotting with x right now in my head, plus 4 times negative 48 does in fact give you 0. If I take it now and dot it with y, I get negative 48 minus 48 plus 16 times 6, which is also equal to 0. So that's good. So we're supposed to find 3 vectors. I think I just found one. 24, negative 48, and 16. Now remember, if you've got vectors x and y, and you find the vector that is perpendicular to both of them, okay, it might look like this, okay, perpendicular to this vector and this vector, then any scalar multiple, any vector that has the same direction as this vector or opposite direction will also be perpendicular. So one way to get another perpendicular vector would be just to swap the signs and have it go the opposite direction instead. Another thing you might realize, these are all divisible by 4. Why not shorten this up? Okay, divide by 4, you get 6, you get 12. You get negative 4. There's another one. Okay, they're also all divisible by 8. Okay, so I could have gotten negative 3, 6, and negative 2. There's another one. So already I've gotten, I think, answered the problem here. That one there. There's another one. There's a third one. And there's a fourth one. There's no right or wrong answers to which 3 you would pick. I would certainly think, though, this one here often is the one that we're most interested in. It is perpendicular to both vectors, and it's as small as possible while still having integer vector numbers. Okay, I could also look at a unit vector. I could normalize that and make it have a magnitude of 1, but it wouldn't have nice integer values if I did that. And then, of course, the other one that's similar to that would be this one right here. So there's yet another answer. You might even say this is the best one because it has the least negative numbers in it, or the first one is positive. I don't know. It doesn't matter. There's 5. That's enough for now. So far in this lesson, you should notice that everything that we dealt with was talking about vectors defined algebraically. And we've sort of talked about geometry a bit in a sense that we've said, well, geometrically speaking, the cross product is a vector perpendicular to both. And the formula that I gave you right in the first page tells you, how to calculate the components of that vector. And then I showed that it would, in fact, be perpendicular to the other two vectors. But we haven't really talked a lot about geometry. So if I were to look at, let's say, A crossed with B, and let's say that we have the angle theta, and we'll say this is vector A and this is vector B. We know that A crossed with B is perpendicular to A and B. So if these are drawn on your screen or on the board, on a piece of paper, then does A crossed with B go into the page or does it go out of the page? Okay, it has to be one or the other. And how long is it? What it's with magnitude? Are there any rules about that? And the answer to both questions is yes, there are rules. The direction of the cross product is given by what's called a right-hand system. So if you take your fingers and you wrap them from A to B, your thumb on your right hand, so take your right hand, this is my right hand. I don't know if that's what it looks like on your screen, the mirror image or whatever, but A cross with B, okay? Take your right hand, wrap your fingers from A to B, and your thumb will point in the direction of A cross with B. So if you think about that first one, does this one go into the page or does it go out of the page? It goes into the page. I'm calling this a page. Into the page. Okay. If I were to have them the other way and I say, now this is B and this is A crossed with B, so start at A and curl your right hand fingers to B, your thumb points out of the page. So now it goes out of the page. Now they call this a right-hand system. Guess what else is a right-hand system? Is almost all screws are thread using a right-hand system. So if you were to go take a screwdriver or a wrench and go from A to B, okay, like this, that is going to tighten something or drive the screw or the bolt or whatever it is into the page. Here, if you were to go from A to B, that's going to loosen it or bring the screw out of the page, okay? Righty-tighty, okay? Lefty-loosey, if you've ever been told that using a wrench or a screwdriver or whatever else, it's the exact same thing. So that's kind of convenient that way. The other thing that is true is the magnitude of A crossed with B will always be equal to the magnitude of A times the magnitude of B times the sine of the angle between them. So that is always true. Okay, this is this is sort of hidden in this handout, but this is a really important definition as well. So if you want to know how large the magnitude of the cross product is, it would be the magnitude of both vectors multiplied together times the sine of the angle, not the cosine, that's dot product, but the sine of the angle. So in a way, we have two different definitions for cross product. The first one is this formula right here. That's the cross product. Okay. The second definition, geometrically speaking, we can say that the cross product is a new vector that follows the right-hand system rule, okay, is perpendicular to A and B and has this magnitude right here. Now, I'm not proving why this is true. It is in your textbook if you want to read about it. It is on the University of Waterloo courseware site if you want to see the proof for why this is true. It's a lot of algebra. It's a long proof. It's very tedious. It doesn't require a whole lot of Like, it's not super difficult, but it's time consuming to go through it. I've decided to leave it for now. We're not going to do it. I'm just going to have to take take my word for it that this is always true. Okay, that's it for the cross product. There's some questions that you can try, and make sure that one thing I'd encourage you, understand this idea, that this part here, this is always true about the cross product, and how we calculate the cross product, is done up here as an example, and make sure that you're checking. When you do cross product, always use the dot to make sure you haven't made a mistake. In class, I'll often make a mistake, which works really well in the lesson, because I go to do the dot product, checking this vector, and you see that I've made a mistake and we have to fix it. So, okay, that's it for this lesson.